In this video, I will derive the Planck's radiation formula for blackbody radiation through his original approach. It will let you know how the idea of quantization of energy and the well-celebrated first quantum mechanical constant, the Planck's constant, crept into the calculations. The understanding of Planck's theory and the original derivation of his formula for explaining the curve of blackbody radiation first needs the formulation of energy distribution among the different harmonic oscillator and thermal equilibrium. This is in fact a problem of statistical mechanics. And in this video, let's try to understand the mathematics behind the idea of Planck's theory, which will of course also let us know how the Planck's constant appear in the theory. Although the modern textbooks derives Planck's formula through an easy approach by using Boltzmann distribution function and the formula for the number of modes that I obtained in the video for deriving Rayleigh Jeans formula. However, here I will try to derive it through the original approach Planck followed. Although this approach is somewhat cumbersome, but it will give us a taste of how Planck's approach to solving the problem. And of course, it will let us know how Planck visualized the problem. The first assumption of Planck's theory was about the constituents of the walls of a black body. That is, he assumed the constituent to be harmonic oscillators. We know from elementary physics that the energy of harmonic oscillator can be expressed in the form E equals P squared divided by 2m plus half beta x squared, where beta is a constant and is identical to the spring constant for a spring. P is instantaneous momentum and x is instantaneous and x is instantaneous position. So the first term in equation 1 in fact represents the instantaneous kinetic energy of the harmonic oscillator, and the second term represents the instantaneous potential energy of the harmonic oscillator. We also know from our college physics that the frequency of oscillation of a harmonic oscillator in terms of beta and mass m can be expressed in the form nu equals 1 over 2 pi square root beta divided by m. According to classical statistical theory, the differential number of harmonic oscillator at an absolute temperature T in a differential position dx and differential momentum dp can be expressed in the form dn equals n sub f times c times exponent minus e divided by kt times dx dp, where nf is the total number of harmonic oscillators in the range from 0 to differential dx and dp, c is another unknown constant, and k is Boltzmann's constant. In order to get benefited from equation 3, we need to eliminate both dx and dp in favor of directly measurable quantities, as they both cannot be directly measured in the present scenario. To this end, let us construct a geometry representing the instantaneous position and instantaneous momentum of an oscillator by constructing an xp plane with Cartesian coordinate x and p, where x points along horizontal and p is along the vertical. In this geometry, the product of differential position dx in differential momentum dp is a differential area dx times dp of the whole plane. And the absence of any external forces means at thermal equilibrium, the motion of oscillator will describe a curve on which x and p varies in such a way that the energy E should remain constant. Since geometrically equation 1 is similar to the equation of an ellipse, therefore such a curve in the xp plane could be in An ellipse with its instantaneous radius or axis represent the energy of the oscillator. So the motion of an oscillator could be described by an elliptical curve of the form shown in the figure. In this geometry, different ellipses will correspond to different energies of the oscillator. In other words, the energy of oscillator in this geometry varies from curve to curve. If E stands for the energy of an ellipse, then the energy of the subsequent ellipse would be E plus dE. That is, the strip of differential area dA can be linked to the differential energy dE, or the change in energy of the oscillator dE. And each point on a single curve then represents the instantaneous state of the oscillator with fixed energy E. So instead of dx dp, we can process equation 3 by defining a differential area in this geometry. Using the formula of the area of an ellipse, in the present case we can write it as A equals pi times p sub m times x sub m, where Pm and Xm stands for semi-minor and semi-major axes and represent the maximum values of position and momentum P. As can be seen from the figure, when P equals Pm, then X equals 0, and similarly when X equals Xm, then P equals 0. So using these set of values one by one in equation 1, we can write E equals P sub m squared divided by 2m plus xm equal to 0, so the second term is 0, and arranging this equation will give me P sub m equals square root of 2me. Similarly, substituting Pm equal to 0, I can write E equals half beta xm square, which leads to xm equals square root 2e divided by beta. Putting these values back into equation 4, the area of an ellipse can be expressed as A equals pi times square root 2me times square root 2e divided by beta, which can of course be arranged into 2 pi e square root m divided by beta. Again, for a harmonic oscillator, both beta and m are hard to be measured. Therefore, we need to replace them through a measurable quantity, and that measurable quantity is frequency, which can be measured in terms of wavelength. So using equation 2, the loss equation can be expressed in terms of frequency of a harmonic oscillator in the following way. A equals 2 pi e times 1 over 2 pi nu, which in fact can be expressed as the ratio of energy to frequency of the harmonic oscillator. Now, both frequency and energy of the radiation are directly measurable quantity. Therefore, the area A can be measured using equation 5. The differential area of a strip between two neighboring ellipses can be obtained by differentiating equation 5, which leads to dA equals dx times dp equals differential energy divided by frequency nu. Now equation 3 for the differential number of oscillator with the help of equation 6 can be expressed as dn equals n sub f times c times exponents minus e over kt times de divided by nu. And this can be put into the form n sub f times c sub 1 times exponent minus e divided by kt times differential e, where I have defined c sub n equals the ratio of c and frequency nu. Equation 7 gives the number of oscillator having energy between E and E plus dE. So I stop this video right over here and will continue the rest in the next video.